Okay, what we're going to do is take a look at the next model of the atom, and what we're going to call it is the quantum model. So just as a quick review, we talked about Rutherford and his model. He put that nucleus at the center with all the mass at the nucleus, and it was positively charged, and he put those electrons around the nucleus, not in much of a structure. Then we talked about Bohr, and with Bohr's model, he had the nucleus at the center, and those electrons, instead of being just randomly placed around the nucleus, he put those electrons in energy levels. We said that each energy level had a specific amount of energy, so if you put energy into the electron to move it up a level, when it fell, it would release that energy it would release its energy at a certain wavelength corresponding to a certain color. And that's where we got those emission spectra for the individual atoms. Well, now what we're going to do is talk about the quantum model. And the reason we don't, there's no I there, and the reason we don't give the quantum model a name like the Rutherford model, the Bohr model, is because many people contributed to the quantum model. However, what we're going to do is take a look at two of the main people who did contribute to the quantum model. Okay, the quantum model takes Rutherford's idea of the atom. It applies Einstein's and Bohr's idea of light to the electron and describes the atom in terms of the electron being described as a wave as opposed to a particle. And this gets pretty complicated, so you may need to watch this vodcast a few times. Alright, the first thing we want to do is take a look at Heisenberg's uncertainty principle. We're not going to go into the mathematics behind this, but basically what Heisenberg said was you can never know the exact position nor velocity of a particle at the same time. Now Heisenberg used the term momentum, but basically that we're going to use the term velocity. So the reason this is the case is, let's say you wanted to observe something in a room, and it just might be a person standing over in the corner. To observe that person, the first thing you have to do is shine light on the person. In other words, if the lights are out, you can't make any observations or measurements. So the first thing you need to do is turn the lights on. That light hits the person, comes back to your eye, you can see the person. So now you can make some measurements. Height, weight, etc. Well, the same thing works with particles. Let's say you're trying to see something very small, and you need a wavelength of light that's even smaller than visible light. So let's say you use X-rays to look at this particle. Well, as the energy of that electromagnetic radiation, and you know X-rays have high energy, as that energy gets higher, it's going to interact with the particle more. So for you to make an observation of this particle, you have to shine light on it. That light is going to move or interact with the particle, so it's going to change its position or velocity. So Heisenberg said, as you try to observe smaller and smaller particles, you're going to interact with them more and more depending on the electromagnetic radiation that you shine on them. So what that means is you can never identify specifically where an electron is in the atom. You can't say the nucleus is here, the electron is right there. What you can know is a probability of finding the electron somewhere in a region around the atom. Okay, well, what Schrödinger did was he took that idea and he developed a mathematical model of the atom, and his equations that describe the atom are what we refer to as wave equations. So you can picture it sort of this way. We know that waves, well, we all know what waves are, and if you think of a guitar string and you pluck the string, it will go at different wavelengths and different frequencies. Well, what Schrödinger did was he took this idea and he calculated how the electron would behave as a wave based on the idea of Heisenberg saying you can't know the position and velocity of the particle at any point. So Schrödinger described the electron as a wave that moves around the atom. Now this is very difficult and abstract to picture in reality, so you kind of have to think of it in abstract terms. In other words, don't try to picture this wave moving around the atom. You want to think of it as this is the description of where the electron can be. And again, if you go into physics, you would talk about this in more detail. But for us, what we need to know is where is the electron around the atom. So taking this idea one step further, what Schrödinger did was he came up with probability distributions. And if you don't know what a probability distribution is, don't worry about it. Basically what it means is the idea of the probability of finding an electron around the nucleus of the atom. And instead of saying, like in the Bohr model, okay, the electron is in that energy level, what we say is that it's in an energy level, but it's in a region in that energy level. And this is, again, is where it gets a little abstract. So we want to think of the electron in energy levels and then regions within that energy level. So for example, Schrödinger came up with different types of orbitals that are within energy levels. And what he said was that each energy level has that many corresponding orbitals. So the first energy level has one orbital, or orbital type, let's say. The second energy level has two, the third energy level has three, four, etc. And they go in this order. So the first energy level has an s orbital. And you want to think of an s orbital as a region where we're going to find the electron. The second energy level has s orbitals, or s regions, and it has p regions. The third energy level has s's, p's, and d's. The fourth, s, p, d, and f. We're not going to worry about anything past f because then it's purely a theoretical idea. These regions have different shapes. The s region, or s orbital, as we saw in the last slide, is a sphere. In other words, it has the shape that basically looks like a basketball. So if you have the nucleus at the center, the s orbital is a region shaped as a sphere where you can find the electron. The p orbital is what we call a dumbbell shape. Dumbbells are an old term that we used to use for weightlifting equipment, but now they basically have the shape like that. So what you're looking at here is that shape. The reason you see three of them, one on the x-axis, one on the y-axis, and one on the z-axis, is because there are three p orbitals. Let's go back to our previous slide. Each orbital type has different numbers of those orbitals. There's one s orbital, there's three p orbitals, there's 5 d orbitals, and there's 7 f orbitals. So let's just take the first energy level, for example. The first energy level we said has one orbital type, and it's an s orbital. Since there's only one s orbital, the first energy level has one s orbital. The second energy level would have one s orbital. Now there's 3 p orbitals. So the second energy level essentially has 4 orbitals, or 4 regions. One of them we call an s, 3 of them we call a p. The third energy level has 1 s, 3 p's, and 5 d's. So the third energy level has 9 orbitals, or orbital types. 1s, 3 p's, 5 d's. The fourth has 1s, 3 p's, 5 d's, and 7 f's. So we said the p orbitals are shaped like dumbbells. The d orbitals, we're not going to put a shape name to those because those get pretty complicated, as you can see. You've got these clover leaf shapes, and then the last one is like a dumbbell with a donut. So we don't give those a shape. This slide is here just so you can see what they look like. F orbitals even get more complicated. You've got clovers with extra leaves plus double dumbbells with, and they just get very complicated. So again, the shapes are here just so you can see what they look like. Alright, so let's get back to the original discussion. What we want to know is where are the electrons located in the atom. Each orbital can hold 2 electrons. So each orbital can hold 2 electrons. We said there's one s orbital, so let's just picture the s orbital like a block. That's the one s orbital. In other words, first energy level has... Okay, each orbital, we said, can hold 2 electrons. So I'm going to put that symbol as an electron, and I'm going to put that symbol as an electron. So what this block means is that it's representing an s orbital, and it has 2 electrons in it. There's 3 p orbitals, so I'm just going to draw 3 blocks, and they can each hold 2 electrons. So those are the 3 p orbitals, etc. So if we want to determine how many electrons are present in the individual energy levels, if we look at the first energy level, it's got 1 orbital, it's an s orbital, it holds 2 electrons. So the first energy level can hold 2 electrons. The second energy level has an s orbital and the 3 p orbitals. So 1, 2, 3, 4, 5, 6, 7, 8. The third energy level has an s orbital, 1, 2. The 3 p orbitals, 1, 2, 3, 4, 5, 6. 5 d orbitals, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the third energy level can hold 10, 6, 18 electrons. We said the first is 2, the second is 8, the third is 18. So the electrons fill up the energy levels 2, 8, 18, etc. What you can do to calculate that quickly is use the formula 2n squared, where n represents the energy level. So if I said how many electrons are in the third energy level, 3 squared is 9 times 2 is 18. How many electrons in the second energy level? 2 squared is 4 times 2 is 8, etc. So as you're trying to determine the number of electrons in the energy level, you can think of it as counting individual orbitals in the energy levels, 2 electrons per orbital, or you can just use this equation. So what we're going to do is just that. We're going to think about electrons placed in orbitals in energy levels. And again, I know this is a little bit complicated, but as you do this and as you do the practice problems, this will become a little bit more clear. So how many electrons are possible in the fourth energy level? We can do this 2 ways. 2n squared, so 16 times 2 is 32, or you could think of it as the fourth energy level has 1s, 3 p's, 5 d's, and 7 f orbitals. Each orbital can hold 2 electrons, so we've got 2 there, 6 there, 10 there, and 14. Add those up, you get 32. How many are in the third energy level? 2 times 3 squared. 3 squared is 9 times 2 is 18. Or you could think S, P, D, 2, 6, 10, 18. How many are in the second energy level? 2 squared, 8. Again, S and P, 2 plus 6 is 8. So the question might be, what's the point in knowing this when all you need to know is that? That will become clear when we start to write what we call electron configurations. The whole idea is to understand where electrons are located in the atom and why. And then, what do we do with them? And again, I know this is a little bit complicated, so read the chapter in the book, watch the vodcast again, and do the practice problems, and you'll be fine.